Okay, in today's video, we're actually going to be talking about a few sections of Blitzer's Introductory and Intermediate Algebra for college students, sections 4.1, 2, and 3. But 4.3 is really what we're focusing on. We just use 4.1 and 2 to kind of build up, so it makes more sense. So basically, when you have something called a system of equations, it simply means that you have lines. Or actually you can have planes as well, but in this case we're going to talk about lines. So when you solve a system of lines by graphing, that simply means that you're going to graph lines and find out what the solution is. Where do these lines intersect, if they do at all? So there's really three solutions to a system of equation of lines, two lines with two variables. And that could be that your two lines indicated by the red and the blue here, they could intersect at one point, and that one point, written in the form xy, is going to be the solution of the equation, the system. And again, what that means is that that point, whatever value of x and y exists at that point, could be plugged into each of the equations of each line and cause it to be true. So if you plugged in the x value and the y value of that point of intersection, then the left side of the equation would actually be the right side, as opposed to if you chose a point somewhere out here or maybe another point on the line but wasn't the point of intersection. It wouldn't solve both equations. You wouldn't be able to plug in the point for both equations. So it's called the solution there. So there's three options for two lines. They can either intersect at a point, and that would be the solution. If the lines happen to be parallel to each other, in other words, they have the same slope but a different y-intercept, then there's no solution. What that means is that there's no point in nature that you could plug into both equations that would be true for both equations, since they never meet. And then the third option for a solution of the system of equations could be that they are actually the same line. You just multiplied one of the lines by a constant, and so it looks different, but it's really the same line. So we call that overlaying. And so that means that there's infinite solutions. So in graphing, we're going to look at all three of those different options: one solution, no solutions, and infinite solutions. But then when we move on to elimination and substitution, we'll mainly just focus on the one solution, this first option. Okay, so here's how you do it. You look to see what each line is, and you can graph the lines using many methods. You can graph by plotting points. You can graph each line by plotting the x-intercept and the y-intercept, or you can graph the lines by looking at the y-intercept and the slope. It simply just depends on how the form of the line that you're given. Since this is called standard form, in other words, you have ax plus by is equal to c, it's usually easier to go ahead and find the x and y intercepts. So what I'm going to do is, for the first line, that I'm going to call it the red line arbitrarily, I'm going to find the the y-intercept. So when x is 0, then y is 1, and that means that that point corresponds to 0, 1. That's the y-intercept. And in this same line, when y is 0, which is, I'm just finding the intercepts here, x is 2. So that corresponds to 2, 0. So this is for the red line. Now for the blue line, I'm going to do the same thing. When x is equal to 0, y is negative 3. So that is the y-intercept. And then for the x-intercept, where y is 0, I'm going to put 0 in this whole term. When I put a 0 in this type of equation, 0, this whole term goes away, so I can just work with the other terms that are remaining. So when y is 0, I just get that x is equal to 6. So here are the points that I have. So I want to go ahead and plot them on the graph. So I'm going to plot the first one with red, and then the second one with blue, just so it's easy for me to see what's going on. So the first one has an x-intercept of 1, y-intercept of 1, and an x-intercept of 2. And so we can plot this one here. Now when you're solving systems of equations by graphing, it's pretty important that you graph as accurately as possible, because just having the graph off a little bit can really change where they intersect, which means that you can get the wrong answer. All right, so this intersects at the y-axis at -3 and the x-axis at 6. And so we're going to plot the blue line. Okay, and when you do that, the solution to this system of equations is at this point of intersection. And so the solution is where x is 4 and y is -1. And we write it in point format because that's actually the solution. All right, so you try this one. Okay, your answer is here. Okay, all right, moving forward. Now we talked about how there are 3 different possible solutions to systems. One is where they actually intersect at a point. We're going to explore the other 2 options where it's either parallel lines or lines that overlap. In other words, it's the same line that overlaps. So what do you notice about the slope of these 2 lines? Because these 2 lines are written in slope-intercept form, which means you can easily see that they both have a slope of 2, and they both have y-intercepts that are different. So the slopes are the same. In other words, both lines are going to have the same rise over run, but the y-intercepts are different. And so right away, I know that these are parallel lines. So my answer is going to be no solution, but it specifically asks me to graph it. So I'm going to do that. So the red line has a y-intercept of -1 and a slope of 2. So rise over run. And I can do it again just to give me a few more points on the line. And it just makes my graphing a little bit more accurate. When I stretch it out over the graph. And then the blue line has an intercept of +3 and a slope of 2. 1, 2, okay. And so upon graphing, I can reconfirm what I observed by looking at the fact that these are parallel lines. Parallel lines have the same slope, but they have different y-intercepts. So if you work on this one, you'll notice that you get the same thing. They're just negative slopes. Okay, so let's try the next one. This is one where these 2 equations don't look the same, okay? So you might not notice right off the bat, especially if one of them was solved for y and the other one wasn't, if they weren't in the same format. But if you notice, the second equation here can be simplified. In other words, there's a 4 and a 2 and a 6. They are all divisible by 2. So I could actually simplify it, sort of like reducing a fraction. So I would get that the second equation is identical to the first equation. So whether I simplified it or if I just used x-intercept and y-intercept, I would notice that this has the same x-intercept and y-intercept as this line. Or if I rearranged both of them into slope-intercept form, y is equal to mx plus b form, when you rearranged it, you would notice that they have the same intercept and the same slope. So no matter which method you use, it's going to end up being the same thing. So when y is 0, x is 3/2, so about 1.5. And then when x is 0, y is 3. I'm just using my intercepts. Now, even though 1.5 isn't very pretty, it's not like a whole integer, it's still okay to graph it, especially since we're not trying to actually solve the equation, because we just know that they're the same line. So you would notice that the blue line and the red line overlap, and that overlapping, so they have infinite solutions. What that means is that any point on the red line is also going to be a solution for the blue line. So any x and y that you have on the red line, if you plug in that same x and y on the blue line, it will make the blue line true. So if you work on this one, you'll notice that the answer is also infinite solutions. Okay, so let's talk about how to substitute to solve for systems of equations. Now, when you substitute, it's just like it sounds. That means instead of using a variable, you're going to use the expression that that variable represents. Okay, so I'm still using the same method as far as trying to find the answer to the system of equations. Where do these lines intersect? But in this case, instead of graphing it, because sometimes your answers might be fractions or decimals, it's not reasonable to graph every single system of equation, but we can solve it algebraically. So if you'll review the steps, we're going to follow the steps. Now, if you notice, I highlighted that if x equals this expression that's in yellow, that means x is the same as this expression. I can substitute this yellow expression where x used to be. Now, the reason for doing this is because I cannot solve one equation with more than one variable. I have to have only one variable in one equation in order to solve for it. I can't solve for only x or only y if I have both x's and y's in there. But if I want to find out what my point is, my x value and my y value, I'm going to actually have to only have one variable in the equation. So I'm going to distribute. I'm going to combine my like terms. And then solve for y. All right, now remember what I'm doing here is I'm actually trying to solve where do these lines cross, if ever. And so I noticed that if my y value is 4, if I put 4 in for y, it'll work for both equations. But I want the point, I want the final answer, the intersection of these two lines. So I need to find x. Well, if I know what y is, I can now use either equation, but I'm going to choose this second one because it's already solved for x, to find out what x is. And instead of putting the letter y, I'm going to put in 4 because I know that y is 4. So I can substitute. That's called back substitution, which means that you've solved for one thing and then you're going to back substitute it into some original equation. So my answer is 5, 4. Now the reason that I write the 5 first and not the 4, even though I solved for 4 first and then I solved for 5. Remember, when I write a point, I always write the x value first and then I write the y value second, because I'm always going left, right first when I write a point, and then up, down second for the second part of the point. Okay, try this one. Okay. So if you did it correctly, then I substituted in all of this expression, 5x minus 13, everywhere there was a y in the first equation, and I found that x was 3, and then back substituted in the 3 for x and solve for y. And what that means, again, when these directions say solve by substitution, you have this bracket with a system of equations. These equations represent two lines. It means, where do these lines intersect? What point does this line intersect? And if I put in 3 for x and 2 for y in either one of these equations, it would be true for both. Okay, so stay tuned for the next video where I talk about how to solve, not by graphing, not by substitution, but by something called the elimination or addition method. That is in the second part of the video.